Aloha, this is RBrewer with the Hawaii Department of Health. This is a recording of a presentation I originally gave to the Hawaii Association of Environmental Professionals with Eric Jensen from Tetra Tech on June 28, 2017. The title of the presentation was Use of High-Resolution Passive Sampler Data and Large Volume Purge Subslab Vapor Sampling Methods to Improve Assessment of Vapor Intrusion Risk. This is a re-recording of the presentation. I've added some notes based on questions and comments that came up during the original presentation. First, quick references. Our technical guidance manual in Section 7 and Section 13 discuss vapor intrusion. Section 7 discusses collection of soil vapor and indoor air samples. Section 13 discusses vapor intrusion in terms of environmental hazard evaluation. A more detailed review of environmental hazard evaluation in our office's guidance on vapor intrusion is presented in the second guidance document entitled Screening for Environmental Concerns at Sites with Contaminated Soil and Groundwater. Both these documents were updated in 2016. Now, the large volume purge, or LVP, subslab vapor sampling methods I'm going to discuss during this presentation will be added to our technical guidance manual, sections 7 and 13, and also noted in our EAL, or Environmental Action Level Guidance. Let's start off with talking about why we collect subslab vapor samples in the first place. The first kind of obvious is for site characterizations, just to identify the presence or absence of contamination of volatile chemicals under a building. Also very important, we want to try to tie or negate observed indoor air impacts to subsurface sources. This is all part of evaluating potential vapor intrusion risk. Then the data can also be used to design remedial actions. So first, let's go over a few basic facts about vapor plumes, in this particular case subslab vapor plumes. Fact number one is that vapor plumes are not uniform, and by this we mean that the concentrations can vary very widely between different areas beneath the slab or within the vapor plume itself. This isn't really a big surprise to anyone who's done a lot of detailed vapor work, but it's a very key assumption, erroneous assumption, has been made in some past vapor intrusion guidance we'll talk about in a minute. So you see three different examples of subslab vapor plumes here. First is an example of petroleum plume under a slab, looking at TPH data. Second example of TCE vapors under a slab in a larger industrial complex. And the third is an example of PCE vapors under a slab at a former dry cleaner. Now in each case here, 1 to 6 liter Summa canister samples were collected. It's pretty typical of doing subslab vapor investigations, or passive samplers may have been used also to map out large-scale patterns. In each of these maps, the large-scale patterns indicated are probably fairly accurate and fairly representative of true conditions. Another key point to remember or think about is these localized hotspots you see, especially in the middle map and on the map on the very right, that are based on single sample points, could very well be artificial and just reflecting small-scale random heterogeneity. So if you move the sample point over a few feet, you might get a completely different number. So key point here, large-scale patterns are probably representative. Small-scale patterns could be artifacts of heterogeneity and not reproducible if the site was resampled. We see the same thing in contaminated soil. This is a study that DOH did a few years ago. We've given 7 presentations on this, where we collected hundreds of co-located discrete soil samples around individual grid points. This is an example from a PCB site where we tested and looked at inter-sample variability, or variability between co-located samples. And you can see here within just a few feet, even a few inches of each other, the concentration of PCBs reported in the samples can vary quite dramatically, from a low of 4.9 ppm to just a few inches literally away of 2400 ppm. So we see a lot of random variability in concentrations of contaminants in soil when we're testing very small volumes in soil around individual grid points. We'd expect to see something not as dramatic, I would guess, in soil vapor data, but equally important to understand and recognize. This is a big issue. This is the same example here of the PCB site we just mentioned. So each one of these sites we designated 24 grid points, and around each of the grid points we collected 5 discrete soil samples. We also looked at variability within individual samples, so we calculate a range, estimated range of the concentration of a contaminant in a discrete sample around any individual grid point. So what this means is we can go out to any one of these sites, or any site, collect one set of discrete samples at each grid point. We can make a map. And then the question is whether or not that map, the patterns we see in that map, are true or are they artificial. So in this case with the PCB site, the large scale patterns are fairly representative. You can see in the first example here, using Excel, we picked a random concentration within the range for each cell, and then made a map of the PCB concentrations at the site in general. So you can see we have large scale upper part of the site. It seems to be where most of the PCB contamination is. You see all these small hot spots within that area. Are those really real? Let's do this again. We went back again using the same set of data. This time we selected a different PCB concentration at each of the grid points, but within the range estimated for that grid point, and we can get a very different map. Large scale patterns look real, but now you can see the small scale hot spots and cold spots within that area and within the map in general bouncing around. So we can do this again. Large scale patterns are real, small scale patterns are artifacts, and we can keep doing this and we get a similar pattern. So a key point here is that when you're testing very small amounts of any media, whether it's soil or soil vapor, that the small scale patterns again can be artificial, while large scale patterns can be real. Fact number 2 with respect to soil vapor samples, again keeping in mind these points we just made, is that a single random sample points are not reliably representative of intruding vapors. So in this case, we're assuming vapors are entering a building through one or more points, and what we've done in the past erroneously is randomly or collect a random soil vapor sample beneath the slab of a building, and then assume that that one sample represents the vapors intruding into the building and impacting into air. This was used to estimate vapor intrusion attenuation factors. But think about this: if you look at the map on the left, the concentration of the contaminant you get in any given soil vapor sample collected beneath the slab can vary quite a bit. So the number you get in the estimated attenuation factor is really totally random, and you have no way of knowing if it's actually representative of the vapors intruding the building and what the vapor attenuation factor is. This is a big issue that came up with USEPA's Empirical Vapor Intrusion Database. We published a paper on this. See the reference down at the bottom. In this case, the EPA staff compiled data for hundreds of homes and businesses across the U.S. where they looked at indoor air sample data, usually one sample of indoor air, and then they looked at a single sample, typically 1 liter of vapors beneath the building, and used that to estimate an attenuation factor of vapors intrusion into the building. The problem with this is that none of the vapor data are verifiable. So the error in the extrapolated generic attenuation factors is not quantifiable at all. So since none of the individual data points are verifiable or valid, then the database in general is invalid. And you can't fix this with statistics. And the calculated attenuation factors that they use extrapolated from the database, they're lower than what's been estimated by other means. And some people have erroneously taken this to mean, well, they're more conservative, so we'll use them. They would only be conservative if both methods used to estimate the attenuation factors were scientifically valid. In this case, the approach used with the empirical database wasn't scientifically valid, so the attenuation factors themselves aren't scientifically valid or really useful. It was still a worthwhile effort to do, as anyone who's done a lot of field work or research knows failed hypotheses are an important part of science. We've given several presentations on this study that we did in the paper we published. There's a presentation that's posted to our web page. You can see the web link there. So the solution to dealing with this random small scale variability, whether we're talking about soil or soil vapor or other media, is referred to as sampling theory. As someone pointed out several years ago, is that the environmental industry is the only sampling intensive industry that doesn't really have a good concept, or hasn't in the past anyway, of sampling theory. Sampling theory is pretty simple at the basic. Under sampling theory, you designate a specific area or volume of some media, referred to as a decision unit, for sample collection. These decision units or DUs have very specific site investigation questions attached to them. Ideally, you would send the entire volume of the targeted media to laboratory for analysis. This usually isn't possible. Consider, for instance, you're concerned about direct exposure to lead in your backyard. Ideally, you'd send your entire backyard to laboratory. have them analyze it and give you a single concentration of lead. Since this isn't feasible in most cases, in reality we have to collect a representative sample across the entire decision unit. In the case of soil, we do this by collecting a 2 kilogram multi-increment soil sample from 30 to 75 points. Now the purpose of collecting a large sample from a lot of points is to, in this case, the sample will capture and represent small-scale heterogeneity within the targeted DU. We don't have to quantify the heterogeneity, we have to make sure we capture it in our data. A good definition of a decision unit is the volume of the targeted media that you would send to the laboratory as a single sample if you could. So keep this in mind as we talk about subslab vapors and even indoor air in a few minutes. Sampling theory concepts are routinely used to characterize indoor air, even though it's not necessarily laid out in this direction. So I said before that the environment industry is one of the few industries that doesn't really understand sampling theory, hasn't incorporated it. That's not really true for indoor air studies. They do a very good job of this in most cases. Consider, for example, the building on the left. Assume there's some vapor intrusion concern for the lower floors. In this case, the volume of a lower floor targeted room is, let's just assume it's 3,000 cubic meters. The question is, does PC in indoor air that's intruding, or PC in indoor air that's impacted by intruding vapors, pose a health risk to workers? And let's assume a 5-day test of the indoor air is representative of a particular season, whether it's in Hawaii the rainy season or the dry season, or on the mainland the cold season or hot season. So the sampling objective in this case is we want to know what is the concentration of PCE in the air that passes through the building over a 5-day period, or in this case, specific case, the targeted room. It's of our investigation. We may want to be more specific than that. Within this room itself, we may be most concerned about a targeted breathing zone. Also, we have to take into account temporal heterogeneity. There's an example up at the top, a graph Blaine Hartman did continuous sampling of PCE concentration inside of a print shop over several days. You can see all these spikes in PC concentration in the indoor air data. This represents at nighttime when they turned the HVAC system off, the concentration of PCE went up. So we also have to think about not only temporal or spatial variability, we're designating decision units for indoor air, but also temporal variability. So in this case, we're maybe most concerned about impacts to workers during working hours. So in this case, we're still talking about a really huge volume of air, and assuming typical indoor air exchange rates and the size of the room I just mentioned, 3,000 cubic meters, probably looking at about 18 million liters of air flowing per day through the breathing zone. So how do we collect a sample of that? Well, ideally we'd take this entire volume of air flowing through the breathing zone and send it to a laboratory for testing. Of course, we can't do that, so we have to collect a representative sample. So I'm not going to get into detail on how this is done in indoor air studies, but typically they would collect a small number of ultimately small volume samples over the 5-day period or whatever targeted period that they're testing. You assume thorough mixing due to the ventilation system during this period, and it's reasonable to assume your data that result are fairly representative of conditions. So indoor air sampling, again, is a very strong concept of sampling theory, and the data tend to be very reliable. How can we apply this to testing of subslab vapors and to assess vapor intrusion risk? Again, let's start back at the beginning and think about what we really want to ask and what we're looking for. What we want to know is what is the concentration, say, of PCE, whatever VOC we're looking at, in vapors that could intrude a building over a targeted time period through a designated entry point in the building. Or this entry point could be a known entry point in the building where you know vapors are coming up through the slab, or it could be a suspect source area under the slab, and you're assuming an entry point could in the future be located at that place, a crack in the floor or something. Or you may be more concerned about a high risk room. Maybe there's a daycare center somewhere in the building and you're especially concerned about vapor intrusion impacts to indoor air within that specific room. Now, if you don't really know much about subslab conditions, there's no reason to suspect a source area under the building. You may just target the center of the slab or the center of the building. So the question again would be, what is the concentration of the VOC in vapors that could intrude the building over a targeted time period through that specific vapor point? So the next thing we have to think about is, what is your decision? In this case, what is our what is the volume of targeted vapors that we're concerned about. With US EPA default vapor intrusion rate into buildings is 5 liters per minute. This equates to about 7,000 liters a day. So that's a really good place to start. This is the minimum volume of vapors that we really need to get data for. So if we're assuming a 5-day vapor intrusion rate or study time, then the volume of subslab vapors we're going to target for sampling would be 35,000 liters. So ideally, again, we would collect and test the entire 35,000 liters of vapors as a single sample. Or you may want to break it up into 1-day resolution. So we want to test 5 series of 7,000 liter samples. When in reality, of course, we can't send this much vapor to the lab for testing, so we have to collect a representative sample. And again, just like indoor air, we need to capture, but we don't need to necessarily measure the smaller scale variability within the, say, 7,000 liters or 35,000 liter targeted decision unit volume of vapors. And also another point that we got hung up on in the past, which is not really that important, is we don't necessarily need to know the location of the source area where these vapors are being drawn from beneath the slab and up into the building. Think about this, the indoor air doesn't really know where the vapors are coming from or really care where the vapors are coming from. So our question deals with impacts to the indoor air. We're not at this point trying to determine where the vapors are coming from within any given entry point in the slab. So now we know what we're looking for. So how do we actually do this in the field? So we set up a field study for the collection of what we're now referring to as large purge volume or LVP subslab vapor sampling methods last year. We just finished publishing the report. So there was a dry cleaner in Honolulu, Hawaii. They'd gone out of business. They had actually removed the building and just left the slab in place. We had data, I'll show you in a minute, that indicated a PC vapor plume under the building. So this is really impossible to pass up. It's a great research spot. So we use some of our research money we get from US EPA Region 9 to go out and just think of a way to collect representative samples of 7,000 liter subslab vapor decision units at the site. Let's look at some of the past data first. It's out the area of the slab of interest that we targeted, outlined in red. This is a 2002 passive soil vapor sampling study done at the site. 24 passive samplers were installed, and you can see in general some typical small large scale patterns across the site. The map on the left is for PC vapors, map on the right is TCE vapors. Quick red flag pops up. You see the red spots here, and humans are naturally attracted to isolated hot spots. But when you see these isolated hot spots in any kind of environmental media data, you should really be cautious. They could just be indicative of random small scale variability. So if we move that hot vapor sample point over 2 or 3 feet, we could get a completely different number. So again, large scale patterns here might be real, small scale patterns definitely don't want to trust. 2016, this is after they took the building down, another consultant went back to the site and installed 10 points to collect 1 liter Summa canister samples. I should mention also this site was being redeveloped as a rail transit station for a light rail station that's being set up in Honolulu. So in this case, they again identified relatively high concentrations of PC and vapors under the slab, but it looked like the core of the vapor plume had moved. They don't have a lot of data at the site now. It looked like it was more in the center of the slab. So was the original data erroneous, or did the core of the plume shift? Maybe there was some expansion of the vapor plume due to the heating and cooling of the slab after the building removal. Don't really know. It's just confirmed there was a problem at the site, but we really didn't have a good idea of what the vapor plume looked like from a site characterization standpoint. So we went back to the site, again thinking in terms of how we can get a better characterization of the subslab vapor plume. So we're also thinking of the multi-increment sampling methods and decision approaches that we use for soil sampling. So in this case, we took the slab and we targeted an 8,000 square foot area. We split it up into 25 cells for sample collection using passive samplers. And you see this here on the right. Here's a map of the dry cleaner setup on the left. So you see the vault, the boiler, dry cleaning machines were up upper right hand corner. Anyone who's worked at dry cleaners would know this immediate red flag. This is where to expect least you would think you would find most of the contamination. Keep in mind this blue line here down the middle. This was a former diesel tank that fed the boilers. So underneath the slab, there's a pipeline that connected up to the boilers. We'll look at that later on. One thing we're concerned about, again, like we pointed out before, collecting subslab vapor samples, passive or active, was potential for random small-scale variability. So if we collected a single sample within each one of these slabs, we wouldn't know if it was necessarily representative of that grid cell area. So we went to one of the cells within the slab, we're going to install 9 samplers, passive samplers. We only end up being able to install 6 because of thick footing. And we tested these individually just to get an idea of what the variability across very small areas within the vapor plume might be. So in this case, you see one of the points came up 28,000 nanograms PC, and a point just a foot or two away, 62,000 nanograms of PC. So we see roughly a 2 or 3 fold random variability of PC masses, at least, probably representing concentrations within very small areas of the slab. So it just gives you an idea of the presence of random small-scale variability underneath the slab. And this is well known with anyone who does a lot of intensive subslab characterization work. It's just not very well documented. So again, a single point beneath the slab may not be representative of the immediate area around it. So how do you deal with this small-scale random variability across very small areas? We went back to looking at the approaches that we used for dealing with this issue with soil sampling and the collection of multi-increment soil samples, or a single sample that's collected across many areas. So in this case, we had limited funds available for laboratory analysis. So what we did is we installed 4 passive samplers in each one of the 24 now grid cells at the site. And then we retrieved the passive samplers, and from each of the grid cells we combined them for testing into a single sample. So we installed in total over 100 passive samplers at the site. We only paid for 25 or so analysis. So this was used to capture and better represent the random small-scale heterogeneity within a single grid cell and improve the coverage of the site and the reliability of the data while managing the cost. We used the Beacon passive samplers in this particular case to do the investigation. Well, how do we know that these 4 samplers combined were actually representative of the targeted grid cell areas? Again, we used the replicate concept and sampling theory that we also use for testing of soils and decision units. In 3 of the grid cells, we installed 3 sets of samplers of 3 samplers each, or 4 samplers each. And then we tested each one of these sets individually, and then we compared the data for each one of the grid cells to look at the variability between our 3 different data sets. And I guess somewhat surprising, maybe not, the average maximum minimum ratio between the highest concentration and lowest concentration between each of the replicate sets was only 1.3, relative standard deviation 17%. So it looks like we were getting very good reproducibility and precision with a single 4 increment set, if you want to call it that, of passive samplers within a single grid cell. Again, this is very small scale. This is the first time we've done it. This gives you an idea of how it might work. So here are the results. You see the map on the left is the actual resolution of the passive sampler data. You see we assigned a color to each one of the 25 grid cells. Red is high, blue is low. So now we have a much better idea of where the vapor plume is beneath this slab. It's in the lower right-hand half of the slab. Highest concentration is in the former boiler area, the former dry cleaning machine area. On the right-hand side of the slide, this is a map produced by Beacon Environmental. It looks nicer than the map that we made using actual data resolution. In this case, the Beacon just took the concentration of TCE, or PC in this case, identified for each one of the cells, assigned it to the middle of the grid cell, and then produced an isopleth map. This assumes a linear trend between points, which is a dangerous thing to do when you're thinking about discrete samples, but in this case it matched up pretty well with the actual resolution. So I think we are actually seeing linear trends between grid cells, and it seems to be relatively representative of the original data. So the next step here was to designate a vapor entry point for collection of a large volume purge sample. Now we hadn't received the actual passive sampler data at the time that we needed to collect the LVP samples. They were about to remove the slab for construction purposes, so we designated the vapor entry point at the middle of the slab. So this would be a scenario. Let's say you didn't know anything about a particular site you were working on. There's no reason to suspect a source area under the building. Maybe you're looking at groundwater plume passing under the building, so you would just designate a vapor entry point in the middle of the slab. That's what we did here. And our question again is, what is the concentration of PCN vapors that could intrude the hypothetical building put on top of this site in the future, say over a targeted 5-day period through a vapor entry point in the middle of the slab. Again, we're going to assume a vapor entry rate through this point in the middle of the slab of 7,000 liters per day. This is our decision unit volume. So our next goal then is to collect a representative sample of a series of DU volumes of vapors coming up through that hypothetical vapor entry point. So how do you collect a representative sample of such a large volume of vapors? It's a paper published by Todd McAlary et al. In 2010. It's very similar to a pilot SVE test. And I have to say, and I've said before, I thought this was pretty ridiculous when I first saw it, but it turns out to be work excellent in the field. So what they do is they install a vapor point in the middle of the floor, again like a pilot SVE test. It could be 1 or 2 inches in diameter, even larger, and essentially hook this up to a shop vac and turn the shop vac on and purge vapors from underneath the slab through the vapor entry point out the shop vac, and they've tapped into the purge line with the Summa canister. So as they're purging, they open up the Summa canister and collect a continuous sample of the vapors during the purge. So in this case, they're able to purge hundreds or thousands of liters of vapors at a time, and then the sample they collect is going to be representative of the vapors purged during that time period. And before they purge and collect the samples, they seal the floors, cracks, drains, and such in the floor to minimize leakage of indoor air down under the slab and into the vapor entry point during sample collection. And also you can monitor the vacuum at individual collection point, at your vapor collection point, just to make sure you don't exceed a target, 7 inches of mercury, 100 inches of water. And in reality, with the shop vac, I think it's a 6.5 horsepower shop vac, it won't pull more than about 40 inches of water anyway. So you're not going to exceed a maximum vacuum at your point. And also, you can monitor the purge as you're actually purging for oxygen, especially CO2, to look for potential breakthrough to indoor air. Typically, the CO2 concentration under a slab is going to be higher than it would be in indoor air. So if you see a sudden drop in your CO2 concentration during the purge, it could be indicative of a breakthrough to indoor air or even outdoor air. This is the setup that Tetra Tech designed for us to collect a large volume purge, LVP samples as we refer to them, at our study site. Again, overall it's fairly simple. On the right hand side is the vapor intake port. It's what's installed through the slab. On the far left is the 6.5 horsepower shop vac, and then there's a purge train in between. So you turn on the shop vac, it purges vapors from under the slab through the sampling train and then out this discharge stack. And along the purge line, they've installed ports for a vacuum gauge to monitor the vacuum on the sampling point. Also install ports for Summa canisters and several types of flow meters so we can monitor the flow during the purge. Also ports installed to connect PID meters to monitor O2, CO2, and other VOCs during the purge. And they also installed some various valves along the way to dilute air during the purge if needed or adjust the discharge. This is all discussed in more detail in the report that we published for this study. This is what it looked like in the field. The first thing we did in the field was go around the pad and in a targeted area and seal any obvious cracks in the pad, which there actually weren't that many that penetrate the entire depth of the pad. We did have one drain in the pad that looked like it went all the way through, so we sealed it with bentonite. So you see here again, set up, it was raining of course on the day we did this. So here you see the shop vac underneath the tarp. Here's the Subslab Vapor sample point on the left coming up and onto the table. You can see on the table here is a series of Summa canisters. Look at this in a minute. Here's the purge train, and then here's the discharge exhaust for the shop vac. And we're a little bit concerned about discharging subslab vapors into outdoor air. We actually calculated the mass of PC that we anticipated to be in the vapors during these purges. It was just a few drops. And as someone in our clean air branch pointed out, compared to what came out of the exhaust pipe of the car on our way there, this was really nothing, not a big deal to worry about. But just to be safe, we did keep it downwind. And you see also on the pad is a generator that we use to run the shop vac. Now one thing to point out here is we only bothered to seal the drains within the slab. We're primarily concerned, if you're doing this in real life, about leakage, downward leakage of indoor air through the slab during the purge and then back into the vapor point. That would not be realistic in terms of vapor intrusion. But we're not that concerned about leakage of outdoor air into the slab along the slab perimeter during the purge, because this is assumed to mimic natural conditions. So all the vapors, all the air under a slab was originally outdoor air that gets pulled up under the slab as vapors enter the building. So the leakage along the slab perimeter isn't that big of a concern using this approach. You're just mimicking what would happen in nature anyway. Let's take a closer look at the LVP setup. You see the Subslab Vapor sample point in the foreground. We installed a very large point. It's more similar to a pilot SV test. You wouldn't need to do this in real life if you're actually getting an LVP sample in a building. You could definitely scale this down. So you see the PVC pipe extending up from the Subslab Vapor sample point to the top of the table. At the top is a vacuum gauge to monitor the vacuum on the sample point. Again, this goes across the table, hooks up to the shop vac in the back. And the consultant here is monitoring purge meters or flow meters during the purge to determine we reached a 7,000 liter target purge volume. Summa canisters are tapped into the purge stream. So when the shop vac is turned on, the Summa canisters are opened, and then once you reach 7,000 liters, the Summa canisters are closed. We only collected one sample during each of the purge. In general, during the first purge, we collected 2 samples, duplicates, just to compare the results. We're also concerned about leaks above the slab. So the major points, turning points and such in the system were wrapped with isopropyl alcohol soaked rags. We tested for isopropyl alcohol in the samples. So once the first purge was complete, shop vac turned off, Summa canister was closed, unhooked from the purge stream, and then another Summa canister representing the next 7,000 liter decision unit purge was connected to the purge stream. Then shop vac was turned on, Summa canister was open, and the second sample was collected. So we did this through a series of 5 purges, collected 6 samples total, including the 2 samples collected during the first purge. A key point here is you want to make sure that the Summa canister doesn't fill up before the end of your target purge volume is reached. So this you need to test ahead of time, looking at the time it would take to reach your target purge volume and the time it would take to completely fill the Summa canister. Usually at a 200 milliliter per minute flow rate, we were able to collect our samples without filling the Summas up within about 8 or 9 minutes. A key thing with this, collecting the samples actually is pretty easy. It's fairly routine. The biggest issue when doing this approach is just same as soil, is what's your decision unit. So I was really concerned about the decision unit volume. I wanted to make sure that the sample we collected in our Summa canisters were representative of the target 7,000 liter purges. I didn't really trust the flow meters completely. I'm a geologist, not an engineer. So we actually bought a weather balloon, took it out to the site, they hooked the system up to the vapor point, turned it on, and then we ran the discharge into a weather balloon. And once this balloon got up to a diameter 2.4 meters, that was 7,000 liters. So we actually used this to verify the precision of the flow meters. At the site, the pilot test on the point indicated 40 inches of mercury. At the vapor point, the flow meters were indicating a 500 to 750 liter per minute flow rate. So this predicted about a 10-minute time to reach a 7,000 liter purge. So we wanted to make sure the Summa canister would collect during that entire 10 minutes. It turned out the flow meters were actually reasonably accurate, plus or minus 10% compared to our balloon method. I wouldn't recommend doing this in the field, especially on a windy day on an open pad. But it is a useful check, maybe inside of an office before you go out and do this in the field. Well, here's the results. So we hooked up a series of 5 Summa canisters to the purge. We ran a series of 5 7,000 liter purges. And you can see on the right the results of the PCE. So the first sample came back 17,000 micrograms per cubic meter. We ran duplicates during the first purge. The second sample, 19,000 micrograms per cubic meter. This is probably getting within the range of laboratory area versus variability in the field. A very interesting thing here is we see the same thing that other studies have shown in indoor air, is that the longer you test, the higher the concentration is. So sure enough here, by the time we got up to the 5th purge, you see the concentration of PCE in the Summa samples increasing 36,000 micrograms per cubic meter to 50,000 to 51,000. The last sample we collected 54,000 micrograms per cubic meter. So probably if you're just starting to do this, you might think, well, you're collecting a really large sample, you're diluting the hot spots. Well, just like for soil, that's not the case at all. It's actually the complete opposite. The larger the sample you collect, the more of these isolated hot spots that you would typically miss with discrete small volume vapor samples are captured in your large volume purge sample. Compare the data here to our commercial industrial vapor intrusion screening level, 8,000 micrograms per cubic meter. So we definitely have a potential vapor intrusion problem at this site. Leak test, especially looking at CO2 and isopropyl alcohol in the samples that were collected, indicated very minimal leakage. Interesting thing with this site is recall again the diesel pipeline that went under the slab, and look where just by chance where we put our LVP, our vapor sampling point. And recall that the concentration of PC is increasing during the purge. What we think was happening is that during sequential purges over time, the source area or the purge was tapping into this high concentration area in the upper right hand corner of the pad. So that's another key point why it's important to collect large volume samples instead of small volume samples. If we collected a single sample from the center point here, 1 liter, we would have gotten a relatively low concentration of PCE, which wouldn't have been representative at all of potential vapor intrusion risk. So that's it. Just in summary, that high density passive or active sampling definitely improves data reliability, minimizes the chance for artificial hot spots and cold spots and confusion over these issues. It's probably not very realistic to install 100 passive samplers in a slab, but it just gives you an idea of how limited your data might be and the cautions you need to take when you can only install a small number of points within a slab to initially characterize vapor plume under a slab. It's a good way to get better data resolution and data reliability is to combine increments from multiple passive samplers to capture and represent small scale heterogeneity within small areas, and you just get one number for the combined samplers. Very important when we switch from site characterization to assessing vapor intrusion risk to think about what you're looking for. And the first thing you want to do is designate a specific hypothetical, or it could be a realistic vapor entry point in the floor. It could be over a known source area or a known vapor entry point, high risk rooms, center of the slab, or whatever. And then you want to target a collection of a very large volume of vapors that has some risk-based meaning to it. In this case, we're assuming or targeting 7,000 liters of vapors per day intruding into the building. So that's our decision of volume of vapors that we want to get sample data for over multiple days. So potential modifications to the approach: use a smaller diameter vapor point, purge trains. I'm sure you could shrink the system down that we used quite a bit if needed. Also, it'd be useful to have some type of tracers to get a better idea of potential leaks through the slab into indoor air. And also other consultants I've talked to have installed monitoring points around these LVP points and then measured pressure differentials during the purge to see if they can get an idea of where the vapor is being drawn from. And this will give them an idea of what the source area is, where it might be under the slab. This is, again, published. The details of the study are published in a field study of high-density passive sampler large volume purge methods to characterize Subslab Vapor Plumes. It's available on our webpage. We also plan to publish a paper on this approach. Next steps. The field study report, presentation, and recorded webinar will be posted to our HERE webinar webpage. We're going to include a preliminary overview of LVP methods in our Section 7 of the HERE Technical Guidance Manual. We definitely want to get some input from consultants and other regulators on how this approach might work in the field and details on how to improve the sample collection approach. It's already being used on the main. I would say Todd McAlary has been using this approach for over 10 years, but especially at chlorinated solvent sites. One issue that's come up is using this approach for petroleum sites, and how you want to be sure to avoid potential explosive conditions when you're purging large volumes of vapor and running it through shop vac. So thanks, and we look forward to your input.